Hi everyone, my name is Neha Kardam and this is lecture 21 on Introduction to Automation. In this lecture, we are going to learn about AC motors. AC motors, they are highly popular due to their ability to provide rotary power with exceptional efficiency, low maintenance requirements, and outstanding reliability, all at a relatively low cost. Unlike DC motors, AC motors they operate by applying AC power to the motor's stationary field windings. The rotor then rotates through electromagnetic induction, eliminating the need for brushes, which are a common source of maintenance in DC motor. This lack of brushes not only reduces maintenance needs but also enhances the motor's ability to be reliable, and it increases its life. With fewer parts which are prone to failure and no brush dust to contaminate a bearing or windings, AC motors they are renowned for their durability. However, despite these advantages that I mentioned, there's a challenge when using the AC motors in control system. While AC motors they are highly efficient, they typically operate at a constant speeds, which may not suit all applications. Because achieving precise speed control requires adjusting both voltages and frequency, which is a task usually accomplished through specialized electronic speed control circuitry, such as voltage per hertz driver circuits. Uh, so, therefore, in AC motors, they find extensive application across various industries. They are used as a fans, pumps, mixers, machine tools, hydraulic power supplies, and they're also used in household appliances also. Uh, and these AC motors, they come in different configurations also to suit different to suit diverse power requirements. So large motors typically use three-phase AC power, while the small ones they use is just single-phase AC power. Now, moving on to the next, here is a single phase AC system, in which power in this the power is delivered in a cyclic manner with voltage alternating between the two conductors, known as prong A and prong B. During the first half of the cycle, prong A carries a positive voltage relative to prong B, reaching up to 170 volts, as you can see here, 170 volts. Uh, and at a middle point here of the cycle, which is 180 degree, there is no voltage difference between the prong A and prong B. However, during the second half of the cycle, prong A becomes negative with respect to prong B. It's important to note that the power company they typically maintains the voltage of prong B at a ground level. So this is usually maintained at a ground level. Um, This prong B, it serves as both the return path for the current and is physically connected to the metal rod, uh, which is driven into the earth. So, because of this, the wire connected to prong B uh, is referred to as a neutral wire, and that's what we see over here. Conversely, a wire connected to a prong A carrying the voltage is known as hot side. This is called the hot side, and this wire is usually colored black, and this should be handled with caution. So it's worth noting that the proper wiring is important for safety and functionality, and if there is incorrect wiring, it can impose significant risk and it and should be avoided at all cost. Next, we have 120 volts AC power distribution circuit. In this circuit, the third pin, as you can see, serve as a safety ground and is kept is kept separate from the neutral wire until it reaches the actual grounding point. This grounding wire is typically connected to the chassis or motor frame, ensuring that the equipment remains at the same potential as the earth. As you can see, this is connected to the ground, this safety ground. And it's important to understand that the concept of voltage in AC circuit, while the designation that 120 volt AC indicates that the effective voltage, if the power content were constant over the entire cycle, the highest instantaneous voltage on prong A, referred to as V peak, can reach up to 170 volts. And this discrepancy arises because the effective voltage accounts for the varying power content through the cycle. Additionally, it's important to note that there are three common line frequencies used in different regions. So if we talk about the United States and Canada, a 60 hertz frequency is being used, whereas in the rest of the world it uses 50 hertz. And in many aircrafts and shipboard, 400 hertz frequency is being used. And these frequencies, they indicate that the rate at which the voltage alternates, influencing the behavior and the performance of the electrical signal system. Next is the three-phase AC circuit, and in this we have two types of connection. The Y connection, as you can see, this is the delta connection. And this is a three-phase power system connected to a three-phase load. This is a three-phase load. So in this three-phase power is generated by a three-phase generator equipped with the three separate field windings which are spaced at 120 degree apart, and this type of arrangement allows for two possible configuration, and these are the two configurations, which is Y and the delta connections. And one end of the each coil is connected to a common wire labeled as neutral, which you can see in this particular picture. This is end wire, neutral wire, while the other ends are labeled as A, B, and C. So this configuration is commonly used when there is a need for both 120 volt AC and 208 volts AC power distribution. Now here, on the other hand, this delta configuration, it connects the three phase in a triangular pattern. Typically, without a neutral wire, this setup is suitable for applications where only 208 volt AC power is required. But what's the difference between the Y connection and the delta connections? So in Y connection, all the loads in an AC system, they are connected at a single point, often leading to unbalanced loads. A neutral cable is connected at the center, as I mentioned it before, which where the three phase meets. So this is the neutral point where all the three phases meets. And most low voltage distribution lines usually have a Y connection with red, blue, and yellow, and a neutral wire, which you might have seen while working in the lab. In contrast, if we see the delta connection arrangements, the three phases in a triangle without a neutral cable, and here the phase voltage is equal to the line voltage. So phase voltage is equals to the line voltage with respect to the ground, and however the Y connection, the phase voltage is basically the line voltage, and line voltage is with respect to the ground. And so in Y connection, phase current and the line current are equal, while in the delta connection, the phase current is under root 3, is basically equal to the line current by under root 3. Now moving on to the next. This is the three-phase AC waveforms. In a three-phase AC system, if all the load impedances, let's say Z1, Z2 and Z3, we have three impedances the way we saw earlier. Let's say these are the three loads we are considering this. If they are identical, the system is considered balanced. In such scenario, there would be no current flowing in the neutral wire. This balance allows for efficient power transmission and operation of electrical equipment. In Y connected three-phase power, which is commonly used for distribution within the facilities, the presence of neutral wire in the Y connection separates the single-phase load to be connected or disconnected as needed. However, in the delta connection systems which lacks a neutral wire, it doesn't have a neutral wire, the balance is inherently maintained in that type of connection. So when three-phase power is transmitted over a power line, the power company typically uses three wires. Upon reaching to the site, so when they reaches to the site on the other end, the power can be easily converted to Y connected power using a special transformer designed for this purpose, where either it can step up or the step down the voltage. So it's important to note that the balanced nature of three-phase system, it contributes to their efficiency and reliability in various applications, from industrial machinery to commercial facilities. And here you can see in for Y connection, the line voltage is equals to √3 of the phase voltage, where line voltage is the three-phase line voltage between any two lines, whereas the phase voltage is the voltage across one line, which for a Y system is also a voltage between a line and a neutral. Now let's see the three-phase delta Y transformation, how we can make this transformation. These are basically designed to convert three-phase power between delta and Y connection. It caters to different voltage and current requirements in power distribution system. In delta Y transformer, the primary winding is connected to the delta configuration, as you can see here, while the secondary winding is connected to the Y connection. And this arrangement allows for flexibility in voltage transformation and distribution. One common application of delta Y transformer is in the power distribution network, where they facilitate the conversion high voltage three-phase power transmitted over a long distance to into a lower voltage Y connected power, which is suitable for distribution within the facilities. And this we also discussed in our in the previous slide. So the delta Y transformers, they are used in various industrial and commercial settings to match the voltage levels and also balance the loads across three-phase systems, and they ensure that we have the efficient, reliable operation of all the electrical equipments. Now comes the electrical safety, which is the very important aspect in electrical engineering. So understanding the risk associated with electrical current is essential for safeguarding against any potential life-threatening hazards. Large currents exceeding 2 ampere, when we talk about when the current is more than 2 amps, they have the potential to cause severe burns, leading to slow or non-healing injuries. Current between 1 and 2 amps can damage nerve centers, potentially causing temporary or permanent paralysis, and in some cases can be lethal if they affect the heart. Even smaller current, ranging from 100 to 200 milliamps, can induce uncontrollable muscle fluttering, with potentially fatal consequences if the heart is involved. So if the current flows through the heart, then it will become very fatal. So currents between 25 to 75 milliamps may result in unconsciousness. But how does current enter the body? So the answer is by touching two different electrical potentials simultaneously. It typically has the high voltage and it has the high voltage and the ground. So when the body completes the circuit when the body completes the electrical circuit, so the current flows through it. The amount of current depends on the voltage and the resistance of the body. So the dry skin offers some resistance, but wet skin significantly reduces this resistance and making shocks more severe. So to mitigate the risk of electrical hazards, it's crucial to implement safety measures. And in high voltage areas, using rubber mats on the floor, wearing gloves, and using non-conductive fiberglass ladders can help reduce the possibility of someone getting shocked. Also, before working on electrical equipment, always ensure that the power is turned off. As an extra precaution, temporarily jumping the high voltage line to ground can provide protection, and in some cases, in in uh, in some cases, someone in case if they turns the power back on. So in that case, high voltage, if it can be connected to the ground, can provide some protection. So next we have is a ground fault interrupter. So ground fault interrupter is used for life protection. It prevents shock hazard, particularly in bathrooms and around waters. So this is the circuit for that. Here is the circuit breaker and sensor circuit is connected, and from the power lines in between the load and the power line, this ground fault interrupter is connected. So without a ground fault interrupter, a person who touches a hot wire while standing in water or in a wet floor will get a shock, because his or her body provides electrical power to the ground and it completes the circuit. So they might get the shock. So this ground fault interrupter circuits, they open circuit breaker quickly if it senses more current is in the hot wire than the neutral wire. Indicating that the current has found an alternating path to the ground, that is through someone's body. So this type of ground fault interrupter for equipment, it is basically used for equipment protection, is to prevent equipment damage and possibly fire due to internal arcing. In the normal, under the normal circumstances, a current should not flow in the safety ground wire when the circuit is working fine. So this was about the ground fault interrupter, and this is the end of the lecture. Thank you so much for listening to me. And there are some problems at the end of this lecture which you can do it on your own. Again, thank you so much for listening to me.